In this video, we're going to talk about recursive neural networks, assuming no background in recursive neural networks. And we're going to talk about handling time series data because that's a great application of recursive neural networks. In subsequent videos, we're going to show how to take these RNNs, especially LSTMs, and apply them to text data. If you haven't watched the earlier videos on perceptrons or multi-layer perceptrons, you may want to go back and watch those first. So far, if you've been following along in this series, you know enough to teach my little friend here to recognize images. But the real world happens over time. So today, we're going to introduce recursive neural networks, and along with that, we're going to introduce time series and handling data that changes over time. I keep saying recursive neural network. I think it's recurrent neural network, right? RNNs. So when we talk about time series data, there actually is a pretty famous data set, maybe not quite as famous as MNIST, but a really common data set to start with. And it's a super exciting data set. It's airline sales in the US from 1945 to 1965. So the goal here is to look at airline sales in the past and predict airline sales in the future. And actually, here's a graph of that data set that you can look at, and you can see that there's sort of two patterns happening at the same time. First, airline sales overall are rising, but there's also a strong cyclic seasonality component. So how do we use neural networks to model this data? So if you remember, I'm constantly talking about the API of neural networks, and I'm mentioning over and over in my first couple videos on perceptrons that all the data that you input into your neural network has to be fixed size. But with time series, it feels different, right? You have these variable sizes of data. So how do we turn that into a data set with a training set and a test set that we can actually input into our algorithm? So there's one super common, super simple way to do it, and that's called the sliding window approach. And the way this works is we take a window of some fixed size, maybe 10 elements, and we go across, we take the first 10 elements and we put that in the first row of our training data. And then from the first 10 elements, we want to output the 11th element, which we call our label for that data. Then we slide over by one, and so we take elements 2 through 11 as our inputs, and from elements 2 through 11, we try to predict the 12th record in our data set. And we keep sliding that window across, and here we've actually created a data set that's exactly the same as the data set that we input into our perceptron in the very first video in this series. So this is a super common approach and a super simple approach, and it can be extremely effective. So should we go to the code? So here we are, and we need to go into the ML class videos directory, and then we need to go into the time series directory, and then open up perceptron.py. So you recognize a lot of this code at the top. So lines 1 through 10 are kind of the standard boilerplate. And then lines 12 and 13 is actually importing a library that I use to plot our predictions in this code. Line 19 here, I set a parameter called lookback, which is actually the size of the window that we're using. So we're taking 20 inputs and we're predicting one output into the future. So we have a function here, load data, and that actually loads in the data from a CSV, International Airline Passengers.csv. You can easily add your own CSV file if you want to do time series prediction on some other data. Line 34 defines another function called create dataset. And this actually does that thing I was talking about, taking an array of data and turning it into that matrix where you have inputs that are size lookback and an output that's size 1. So as usual, data X is the inputs and data Y is the outputs here. So line 42 actually calls the load data function and puts the airline data into the data variable. So this is a single dimension output, which corresponds to the airline sales at each month. And then if you remember from our perceptron video, all of these things work better if you normalize the data to be between 0 and 1. And so I actually do that in lines 45, 46, and 47, just subtracting out the min value and then dividing by the difference between the max and the min. Now, lines 50, 51, and 52, what they do is they split it into a test and train data set. And unlike with MNIST data or non-time series data sets, I think it's better to split it into chunks. So rather than randomly taking values, we take the first 70% of our data, which is maybe in the past, and we use that as the training. And then we take the final 30% of the data and we use that as the validation set. This is because what we'd really like to do from here is take our data set and predict it on data into the future. So lines 54 and 55 do that transformation I was talking about, where we take the single dimension data and we turn it into a matrix where train X is the inputs and then train Y is the output that we want. And here test X is the input on the test or validation data set and test Y is the output that we're hoping for. Lines 57 and 58 add a new dimension to the data. This is similar to what we had to do to use convolutions on our data in a previous video. They basically just add an empty dimension to our matrix of data. So here we are at line 61, and we're going to finally create our neural network architecture. And it says RNN, but actually this isn't really a recursive neural network. This is the exact same perceptron that you would have seen in the first video. So just like we had to do in the first video, we add a flatten layer that takes our multi-dimensional data and smashes it down into a single dimensional input. And then line 63 adds a single perceptron that outputs a single value based on the input data. And in this case, our activation function is linear, but we could certainly change it to something else. Line 64 compiles that. Here we use our atom optimizer as usual. We actually don't use categorical cross entropy as our loss. You might want to stop and think about why. Do you remember why? Well, we don't use categorical cross entropy for our loss because we're actually predicting a scalar value. We're not predicting a category. So in this case, because we're predicting a number, we use mean squared error, but you could try something else like mean absolute error if you wanted to. And our final line, 65, actually does this fit. So here, train X, as usual, is the input data. Train Y is the labels we want to predict, or the future value of this time series. We're going to train it for 1,000 epochs because we have a pretty small data set, and we're going to use a batch size of 10. We also pass in our validation data, test X and test Y, and then we have some functions to actually plot what's happening as the system runs. So you can go back into your terminal and you can run python perceptron.py. So you can watch it run here. It's super, super fast because it's a perceptron on a small amount of input data. Check this out. So here the blue line is the training data and the orange line is the data, the test data that we held out. And the green line is the prediction that our system is making. And you can see that our predictions here are pretty reasonable. So the way we do these predictions is we keep feeding in the predicted input as input into the next prediction, right? So if we kind of get off, these things can go haywire. But in this case, our little perceptron with a small window of past data is actually doing a pretty reasonable job of forecasting airline predictions. So we're going to make this thing more complicated, but actually this is not a bad result on a data set like this, and you could really use this in production on certain types of time series data. Okay, but you guys didn't come to this video to learn about using perceptrons on time series data. I'm sure that what you care about is recursive neural networks. But you might stop and think, why do we use recursive neural networks at all, right? What's better about a recursive neural network than a dense perceptron? What is it missing? And I think what these perceptrons are missing is the element of time. So if you scrambled the inputs from 1 to 20 in the lookback that we fed into this perceptron, it wouldn't make any difference in the accuracy of the algorithm. If we scrambled the past, it has no effect on the prediction. So we're putting a lot of work into our perceptron. We're making it learn actually causality of time in a way. So there's lots of parameters, and on the small data set, it works okay, but it struggles on bigger, more complicated data sets. And anytime you can put some knowledge that you have about the world into the architecture of your model, it's gonna generally make the models do better, especially when the data sets get more complicated. Recursive neural networks generally, they take the same kind of input as the dense neural network, right? So they take in a set of data over time in numbers or vectors of numbers, and they output a single number or a list of numbers over time. But now here's the difference. They actually keep a state that they pass through to themselves. So this is a diagram of a simple recursive neural network, and it's basically taking a state from the previous neural network and it's outputting something. Now, what happens inside of these recursive neural networks is different depending on the type that you use. So in Keras, you'll have a simple recursive neural network, you'll have an LSTM, and you'll also have a GRU. Those tend to be the most common neural networks that you'll see in the wild. So let's start with the simple recursive neural network. How does that work? So our simple recursive neural network, it takes in an input. In this case, it's a single number, but it could be a larger dimensional thing. And it also passes through some state. And also in this case, it's a single number, but it could be larger later. So now it has two inputs, one from the outside and one from its previous self. It takes those two numbers and it actually does the exact same calculation as a perceptron. So a weighted sum with an activation function, and it outputs a single number. It then takes its output and it passes it into the next recursive neural network. And now that network takes in a 4, and it also takes in the output from the previous one. And it does the exact same calculation with the same weights. And it does that 10 times or 20 times, or as long as our window is. And at the end, it outputs a number, and we take that output to be its prediction of the next value. And we can do all the same things we did with a perceptron or a CNN, where we do backpropagation. In this case, it's called backpropagation through time. And we find the best set of parameters to make this output prediction exactly what we want it to be. So let's see how this looks in the code. So that was a lot to take at once, and you might have missed a little of that. But it's actually very easy for us to swap in a simple RNN for the perceptron that we had. You can open up rnn.py, and you'll see that there's only one small change I made. Before, where we had flatten and we had a dense layer, I added simple RNN, and then I have this one number here. And what that one number means is that its output and also the thing that is passing from cell to cell is a single dimensional thing. And that's important because our output dimension is actually a scalar. It's a one-dimensional number at each time step. So we can run this RNN by typing Python rnn.py. And I also save this to save us time. So here we have our blue line is the training data of this airline time series. And then the orange line here is the actual data. And the green line is our prediction with the RNN. And you can see that this prediction is a lot worse. It's not predicting anything like what the data shows us. So here's a great case where we can look at the loss and we can look at the validation loss. And we can see that those are both improving. So we can let this thing run for a while. But actually what happens if we run this over time is that it never learns to actually fit our data. So here's what other videos don't show you, right? This is a non-working recursive neural network. And so what I'm going to show you here, which I think is really important, is how to debug this problem and how to fix it. So one thing I like to do when I'm dealing with a broken neural network is I like to run it on really simple data. So how could we make this airline data even simpler? Well, one way is to use synthetic data. So I actually have a little program, make-sine.py, where I just output a sine wave. I just want to see, can this neural network model an actual sine wave? So if you go in and you change this load data thing to take in a parameter sine, S-I-N, now our model is trying to model a sine wave. This seems like it should be almost the easiest time series data to model. So let's make that change and let's run our program. Whoa. And so you can actually see here that this neural network is not modeling the sine wave at all. In fact, it's predicting -1 for all these values of the sine wave, which it never even sees in the data. So first of all, how is this thing even predicting a -1? How is that even a possible prediction that this thing could make? And it actually reminds me that I forgot to tell you something about these neural networks, which is that they have a new activation function typically. And we'll get into why that is, but this activation function is called a hyperbolic tangent. Okay, so I don't know how many people remember hyperbolic tangent from maybe their trigonometry class. I'm not sure I had thought about it much until I saw it appear in a neural network. The important thing to know about hyperbolic tangent is that it's basically like a sigmoid function, but instead of going from 0 to 1, it goes from -1 to 1. So in this case, a really negative number will output a -1, and a really positive number will output a +1. And LSTMs and GRUs, they use hyperbolic tangent activation function like crazy, so Keras actually makes the default activation function this hyperbolic tangent, even though it's a simple RNN and it probably doesn't really need to have that. But now, the big issue here, the reason that this RNN can't learn such a simple thing is that it's actually only passing across a single parameter, right? So actually just passing one number from point in time to point in time is not enough to even learn a pattern as simple as a sine wave function. So what we need to do is we need to let it pass through more state, more than just one single number. So we can actually do that by changing the 1 into a higher number. So let's do that in the code. So here on line 62, where we see simple RNN 1, let's try changing that to a 5. So now it's going to pass across 5 numbers instead of 1. And maybe that can encode the state of affairs. So we get an error. This is what the other videos don't show you, these errors, right? So I'm gonna debug this with you, but you might want to stop the video and think about why we got this error. Because this is a really common error to get when dealing with neural networks of any type, right? It's a dimension error. So it was expecting simple RNN to have shape 5, but it got an array with shape 1. So what happened here? So what's going on? Well, so we're outputting a 5-dimensional thing, but actually because if you look at this diagram, right, so simple RNN, it actually outputs the same thing that it's sending to the next cell in the recursive neural network. And so it's outputting a 5-dimensional thing, and we can't use that. So how do we turn this 5-dimensional output into a single-dimensional output? Well, one way to do it is to actually just add a dense layer at the very end, and this is super common, right? So what this is going to do is it'll take the 5 numbers that this network outputs, and then it'll add a final perceptron that does a weighted sum that takes it down to a single output. And so we can do that here by just adding a line that says dense. So we add model.add dense 1. And we could actually add a different activation function if we wanted to. So by default, it'll use a linear activation function, which will let it output any number. But we're trying to do a sine wave. We add a single line, model.add dense 1, that adds our perceptron at the end. And we could actually add a different activation function here. In this case, our data is normalized to be between 0 and 1. So I think a sigmoid probably makes sense. So let's say activation equals sigmoid. Awesome. Let's run this network. And so you can see at first, this network is actually doing already a much better job of modeling the sine wave. So at first, it seems to get it, but it kind of dampens over time. So it doesn't actually swing as much as the sine wave swinging. And this sort of shows you actually how modeling time series is tougher than modeling other things, because errors that you make in the beginning of predicting the future then feed in to your model and cause further errors as you predict out further. So this seems to start okay, but then get bad. But then, after around 100 epochs, it's starting to really model the nature of the sine wave. So I think we can stop and say that this network architecture is working much better than the previous one that we had. And then we can take it and we can try it back on the airline data. So now that we've debugged our model, let's go back to the original data set by just removing the sign here. And let's try running it. Cool, and so you can actually see that this is starting to model this airline data much better. And over time, it gets better and better and captures more and more of the way that the airline sales data set actually really looks. And so I know you came here for an LSTM, and we're going to go deeper in the next video into how LSTMs really work. But I want to show you, just as a taste of how easy it is to switch this simple RNN to an LSTM. So if we go back into the code, into rnn.py, all we need to do is change this layer where it says simple RNN to LSTM. Go into our terminal and we type python rnn.py, and we're running our first LSTM. One thing you'll notice about this LSTM right away is that it runs a lot slower than the simple RNN, and it runs much, much slower than the perceptron. And that's because there's a lot going on here, and that power is going to be really important in some of the subsequent things that we talk about, especially when we run them on text data. Because if you think about it, one way to look at text data is just a really complicated type of time series data. Today, we saw how to take a recurrent neural network and use it inside Keras on time series data. And we even saw a little bit about how to debug a recurrent neural network. And at the very end, we swapped in for our simple recurrent neural network an LSTM, which we're going to use quite a bit into the future. We also learned how to take data and turn it into the format that you need in order to apply any type of time series algorithm.